Welcome back, everybody. We're here for the second part of our product and quotient rule notes for 2.3. So we're going to look at the quotient rule. So the quotient rule is going to be a little bit more complicated looking than our product rule, but again will become pretty much standard practice once you've gotten used to it and done enough examples. So let's go ahead and look at our definition of the quotient rule. So if f and g are two differentiable functions for all values such that g of x is not equal to 0, so we do have to worry about division by 0 now if we're taking the quotient. So we have to make sure g of x is not 0 at that value of x. Then what we end up with is when we take the derivative of the quotient of f over g, what we end up is with this expression. So we have g f prime minus f g prime all over g of x squared. So one note that I will put here that is kind of interesting is that this is almost the product rule on top, right? It's not quite the product rule, but it's almost the product rule. It's the product rule with a minus sign instead of a plus sign, right? Because we have the first function's derivative and the second function, and then we have this first function and the second function's derivative exactly. So if we just put a plus here, then we have the product rule on top. But it turns out we get this opposite value of that product rule. So that is one key difference. Now, obviously, you can think of this in a lot of different ways. There is a typical mnemonic that I recommend students use when they are working with the quotient rule to kind of remind themselves of what it is, similar to the quadratic formula song, that sort of thing, where it's repetitive and you can say it again and again and again, and it will kind of stick in your mind after a certain amount of time. So I have it written down here on the bottom. And so the way to remember it is low d high minus high d low. It says all over low squared, but we should change that, because that's how I learned it. But one that's a little bit better because it rhymes. Is low d high minus high d low denominator squared below. So again, low d high minus high d low denominator squared below. And so the low and the high are just referring to the location of those two functions. So high meaning the numerator, low meaning denominator. So again, low d high minus high d low denominator squared below. Low d high minus high d low denominator squared below. So you can kind of go through that, use it a few times, get it in your head, and then as you practice with it, it'll get better and better. But also just note that up on the top there is really that product rule as a difference, right? So product rule as a difference is up in the numerator. So, all right, let's go ahead and get to some examples using that kind of traditional mnemonic. So we'll start with number 1. So we've got this standard rational function. So we've got two linear terms in the numerator and denominator. So for f prime of x, so again, remembering that this is your high function and low function. So we're going to get low d high, so derivative of the numerator is just 2, minus high d low, derivative of the denominator, all over low squared, or denominator squared below. So that's going to be our derivative for f prime. I should note also the proof of this is in your textbook, and it's going to look just like our product rule proof, only all of these terms will be f of x plus delta x over g of x plus delta x. And we still add and subtract a convenient quantity, and it follows almost exactly the same as this, only the expressions are different. So it's not too bad to prove, but it is a little messy, but you can look that proof up if you're interested. So now we just need to clean it up a bit. So let's distribute in the numerator. So we'll have 2 minus 6x minus, now I have a negative here. So what I'm going to do is I'm going to combine those two negative signs. So we're going to make those pluses. So we'll get plus 3 times 2x is 6x, And then 3 times 4 is 12. All over 1 minus 3x squared, which is, we get cancellation of the 6x's, which is nice. And we get 14 over 1 minus 3x squared. So that is our derivative expression. Okay, so we can look at number 2. Again, we'll do the same thing. So g prime of x is going to be low d high, since the derivative of sine is cosine, minus high d low, since the derivative of 7x minus 3 is just 7, denominator squared below. Okay. And again, now cleaning it up is going to be a bit trickier because we've got this cosine and sine x, so there's not going to be a really nice way of combining everything like the first example, so we'll just distribute everything. So we'll get 14 cosine x minus 6 cosine x minus 14 sine x. So we get that all over 7x minus 3 squared. Yep. And I forgot, it's 14x cosine x, because we can't combine those. So 14x cosine x. All right, so those are the first 2 examples there. And then we'll do the same thing for this third example. We'll take that same graph and consider some derivatives of the quotients of those 2 graphs. So let's label this again. All right, so we've got Q is F over G, so we'll just note that Q prime is going to be low D high minus high, whoops, D low, denominator squared below. All right, so Q prime of 7 then is going to equal G of 7, F prime of 7 minus F of 7, G prime of 7, all over G of 7 squared. And we'll do the same thing for 2, so that's going to be G of 2, F prime of 2, so low D high minus high D low, denominator squared below. All right, and then we can substitute in values from our graph. So we'll start with Q prime of 7 here. So G of 7 is 1. F prime of 7 is 1 over 4. Minus F of 7, which is 5. And G prime of 7 was negative 2/3. All over G of 7 squared, but that's just 1. And then we can combine, excuse me, the numerator. So that's going to be 1/4 plus 10/3. So that'll be, I think, 43 over 12. So you can verify that yourselves. And then for 2, well, what's G of 2? G of 2 is 2. Okay. So we get 2. F prime of 2 is 0. So that's where our parabola is located. And, oh yeah, what's G prime of 2? So G prime of 2 is, oops, is 1/2. So G prime of 2 is 1/2. And F of 2 is 3. So we'll get 3, 1/2, all over G of 2 is 2, 2 squared. 4, so we'll get negative 3/2 over 4, which is negative 3/8. All right. So again, using that formula, but now with a table, or with a graph instead of a explicit function or a table. All right, so those are the two main rules for these notes. Below that, we've got some derivative notation that you're going to see, so higher order derivatives. So we're going to use this prime notation here quite a bit. And really what we're most interested in this course is the first and second derivatives. But we can have the third, the fourth, the fifth. And again, we use that parentheses notation once we get past the third derivative usually. The third derivative has lots of applications in multiple variable calculus because it describes something called the jerk. But for us, we're single variable, so it won't have much application. We can do the same prime notation with f. So f can have the exact same prime notation, and it will follow the same way. And then we've got the variation here, which is the Leibniz notation. So it looks a little bit different than that because we've got dy over dx, but then we have this d squared over dx squared, and the y is on the outside. And again, the reason for that is that d over dx is an operation, just like multiplication is an operation. So if I have like 3 times 3 times 3, one way of simplifying that is to say that this is 3 cubed. Right? So we're saying apply multiplication twice to this number. So 3 times 3, which is the first operation, and then times 3 again. And so we use this notation all the time for multiplication, which becomes exponentiation when we multiply over and over and over again. The same idea is with the operation here. So if I take the derivative of f of x, that's f prime, and then I can take the derivative of that value I just found, right? So I can take the derivative of the derivative. But instead of writing this nested d over dx over and over and over again, we simply just combine these, right? So we just say that there's 2 of those, right? So I'm going to take the derivative twice of this object, which is the function of x. So just a quick little notational note that you're going to see here. And really the ones that we will use most often are going to be these 3. So, and in particular, these 6 up here. So you're going to see these quite a bit. Okay. So notation is there. And then we've got some additional trigonometric derivatives that we're going to look at and derive. So I think I'll stop here for the moment at the end of the quotient rule. And then we'll finish up the notes in the last video. So again, if you have questions, send me an email, come by office hours. Otherwise,